Welcome. In this lecture, which has multiple sessions, we'll explore the Lagrange function and the associated Lagrange equations. The main concepts for this are that the Lagrange multipliers that we explored in a previous lecture add variables to a problem. And specifically, we'll use the Lagrange function to include equality constraints in this lecture. The equations will turn out to impose gradient constraints, or, when we transpose it, vector constraints. And those will produce a linear equation. Our sample problem that we'll consider in this lecture is, imagine that we have a system, a mechanical system that has two springs and one mass, and we want to study what happens when it's in a force balance. The way that we'll study this is we have a theorem from the previous lecture that was inspired by geometry, and we're interested in minimizers, so let's just consider this situation, is that at a minimizer, and let's refer to it as some specific minimizer, there might be more than one, of a function that has a vector argument. And what we'll say is that this is such that a property function at that specific argument value is 0. Then what we have is that the gradient of the function at that specific point is, and we'll introduce a negative sign. There are two conventions. We'll use the negative sign convention. It's a negative Lagrange multiplier times the gradient of the property at that specific point. So this could be a maximizer or a minimizer. We're interested in the minimizer. So if we consider this is a partial differential equation, and it turns out that there's an infinite number of functions that satisfy this. Well, one of the simplest would be, let's say that what we want is, we can see that if we take this over to the other side, that would say that the gradient of f plus mu times the gradient of p equals the 0, 1 form. And we could say, well, suppose that we just integrate that. So one function, one is, and this is the Lagrange function, after the famous mathematician Lagrange, whom we have already explored previously because we like the Lagrangian remainder form of the Taylor series. So the Lagrange function of this problem is, and this is usually written as a script L, this has the vector argument that the objective has, and in this case we only have one property, one constraint, so we'll just write that as a scalar mu, and we will define that as simply, we'll take the objective function and we'll add some scalar multiple of the property function. Evaluated, so these are both evaluated at the same argument or at the same point in the n-dimensional vector space. And what we're saying is we'll define that Lagrange function as simply being the objective plus some scalar multiple. Now, we don't know what that is, and so in general we're going to have to solve for it. So let's now think this through, is that a minimizer of this Lagrangian function, if it's a minimizer, it must be a stationary point. And that's a really key insight, is that this is a necessary condition. It's certainly not sufficient, but it is necessary. So that means we must have, so for this to be a stationary point, what that means is that the partial derivative of the Lagrange function, let's say we're evaluating it at a W star, and the partial derivative with respect to the vector argument has to be a 0, 1 form. That is, it has to be stationary with respect to this bunch of the variables. And it also when we evaluate it at a stationary point, the partial derivative with respect to that Lagrange multiplier also has to be 0. In this case, it's a scalar because the partial derivative of the Lagrange function with respect to a scalar is a scalar function. And we're saying that that has to evaluate to 0 at that stationary point. So we'll transpose these. So transpose into vectors. And the reason that we'll do that is so that we can use ordinary solutions. So when we transpose this one form, that gives us the partial derivative of the Lagrange function with respect to the vector argument, and we'll transpose that. And then we'll take the partial derivative of the Lagrange function with respect to mu. Well, that's a scalar in this particular case. In a general case, there might be more than one property, so there might be more than one Lagrange multiplier. So let's anticipate that. We'll transpose that. And now this is a vector and that's a vector, so I can gather those into one huge vector equation. And then when I multiply that by W and mu, I want that to equal a 0 vector. And the dimension of this 0 vector is the number of entries in W plus the number of entries in mu. So if W is in an n-dimensional space, this 0 vector would have n plus 1 entries in it. And so this is what we want, is that we want to find a solution to this. And the general case, this is a difficult problem. What we'll discover, though, in the subsequent sessions for this lecture is that for a common kind of problem that we're going to come across, this will turn out to be a matrix vector equation.